Great.
Should we start?
Yes.
So it's a pleasure here to introduce Giulia Guidi, who's defending her dissertation. And Giulia got her undergraduate and master's degree in biomedical engineering in Politecnico Milano before she came to Berkeley to continue working in biology, but as well as high performance computing. So her work, which is joint with a number of people in the audience and on Zoom, has to do with how do you do fast genome sequencing on the largest parallel machines available, but also how do you do cloud computing efficiently? So very interdisciplinary. And I will invite any of the other advisors in the audience to say, add anything they like. Otherwise, I'm going to give the microphone over to Dan.
I'm just going to say that I think it was 2017 or 18 when Giulia came to spend an extended internship at the laboratory, Lawrenceburg laboratory, as part of a bigger group of Politecnico di Milano students. And then next year she got admitted to the PhD program. And it was at this time that the long read sequencing was becoming much more reliable and higher accuracy. So it was a great match for the technology and the things that we can develop. And I just want to say that Giulia had been the extended research group's unofficial organizer of things and has taken a lot of roles on pushing people to actually meet outside, despite several of those years being under COVID quarantine. So thank you, and it's yours to speak.
Thank you.
I'll just say quickly how much of a pleasure it's been to work with you for the last, I guess it's been 5 years since you first came, and it's tremendous to see you develop and grow, and the work you've done is spectacular.
Thank you. Thank you so much.
Maybe I will add after all that. I also really, it's been just wonderful working with you over these 5 years, and I look forward to continue to work with you on your new endeavor.
Thank you. And this was perfect, so I got the time to get the microphone back. Okay, thank you, everybody. I'm very, very happy and excited to be here today and to talk to you about my work that I developed in the past 5 years. And the title of my dissertation and of the talk today is Power Algorithms for the Novel Long-Read Genome Assembly using Sparse Linear Algebra. And as I didn't briefly mention, it has been a good match when I started to work on this, because we had these great sequencing technologies and genomics technologies. But the problem is that since this technology became much more reliable and also cost effective, then we needed more compute power and systems to be able to process this. I'm sorry, I'm trying to figure out why this doesn't work. Okay, perfect. And so in this is where high performance computing comes into play. If we think about high performance computing in general, we often think about simulations, if you think about climate and cosmology. But as I mentioned, the fact that now we are able to generate this huge amount of data in genomics and also other sciences, then opens the door to use high performance computing, for high performance computing to be needed in other sciences as well. And to give you an example, this is the cost, this is a plot from NIH from 2021. And on the y-axis, we had the cost of sequencing the human genome, and on the x-axis, the years. And we can notice that in the past few years, the cost of sequencing the human genomes decreased significantly. And the cost is, of course, proportional to the size of the genome. But we can, the fact that we're able to generate much more data, not only, now we require better algorithms and better systems to process this data, but also it's quite interesting because this opened the door a whole sort of new application that maybe was not possible when the amount of data was limited. And this whole application, as you can imagine, goes around human health, and you can imagine how many genomes we have been sequencing, unfortunately, in the past few years. But the application of genomics goes well beyond the human health itself into biofuel production and agriculture. For example, in the context of climate change, you can imagine that you would like to study plants' genome in order to figure out how we can make them more robust to heat and climate change in general. And so just to give you a brief example of the impact that genomics can have on real life, this is a study from 2018 that shows how being able to do rapid genome sequences decreases infant morbidity and also the cost of hospitalization by quite a lot. So like being able to like handle properly this data can have a huge impact on our lives. But in particular, during my PhD, I focus on a problem that is called de novo genome assembly. And we can kind of break it down in two pieces. And the first piece is the assembly part. So the idea is that we have genomic sequences that are shorter than the actual genome of the species that we're considering. And we need to figure out how they go together. So it's like building a puzzle. So we have many small pieces and we need to figure out how to put them together to get the final image that is our genome. But the challenging part stands in the de novo part because we do not have the reference. So it's like someone enters in the room right now, drops a huge puzzle on the floor and then leaves with a box. So we don't know if you're trying to reconstruct a cat, a dog, a landscape, or something else. And as I mentioned, these puzzle pieces are very, very small with respect to the final image we want to reconstruct. And they can contain errors. So the process that we have to sequence the human, like the genomes in general, is not perfect. It improved quite a lot, even just throughout my PhD, but we can still introduce errors. So we might have pieces of the puzzle that look similar, but they come from different regions, or they do look slightly different, but they're actually next to each other. And then the next challenge comes from the biology itself, and in the fact that in the genomes, we have repetitive regions. So we have portion of the genomes that get repeated throughout the whole sequence. And so this makes it very hard to figure out where those regions exactly are. You can imagine that in this puzzle, we have half of the puzzle, 1/3 of the puzzle being a blue sky. So when we have like blue pieces, it's very hard to figure out if it's in the top left corner, top right, or somewhere else. And so the main problem is that if we look at the state of the art, we do find a lot of software that can, with very accuracy and performance, that perform de novo genome assembly. But the runtime is quite problematic, since if we go on mammalian genomes, like even just the human genome, that is not one of the biggest. So just so you know, for example, the wheat genome is like 17 gigabase pairs, and ours is 3. So it always blows my mind thinking about the plants as like these huge genomes with respect to ours. And so, of course, these doesn't really scale well if you want to go into larger genomes. But even if we just focus on the human genome, you could imagine an application where you want to repeat this assembly multiple times on different individuals, or you want to be able to have results in less than 1 or 2 days. And so the goal of my dissertation is to use massively parallel system to make de novo genome assembly faster and make it feasible and practical to use it on large genomes as well. So if we look at the reality check of how software for this kind of computation is built today, what we see is this very complicated type of pipeline. And this is a Canoe assembler pipeline. This is one of the most popular assembler to assemble long genome developed from a group at NIH. And you can see that there is like very complex and no modular. I actually met one of the developers of Canoe. I think it was my first year of PhD. And I was super excited. I was like, oh, maybe I could just work on Canoe and make a faster version. And he was like, you really do not want to put your hands on that software. It's like years and years of software engineering. And if you move one piece, God knows what's going to happen on the other side. So this makes it very hard to just reuse something. Let's say that Canoe does this portion very well. It's just very hard to extract and try to reuse it in your own software. And this also presents a problem in terms of performance and updating the algorithm. Performance, because you might want to do, I might have a better way to do this part, but also in terms of like update algorithms, like data keep increasing, keep changing. And so you might want to introduce new information that you can get from new data set. But if every time that you need to update the algorithm, it takes like 3 years, then it's pointless. So we could summarize this as like the problem in genomics pipeline and de novo genome assembly is the lack of abstraction and modularity. And so with this, I gave you like a first introduction to the problem. And now I'm going to give you like a kind of dissertation overview. So what I did in the past few years. And then I will go a little bit more in details of the 2 main parts. So the first is like de novo genome assembly as generalized sparse matrix multiplication. And it's composed of 3 main parts, but for the interest of time, I will go just in the details of the first 2. And then I will talk a little bit about my work about high performance computing in the cloud, and then I will go into conclusion and future works. So in terms of overview, so the idea in my dissertation is like, if we can map the computation to higher level primitives, that we know how to parallelize, that we know how to update in a faster way, then we can achieve much better performance and modularity. And so here are a few motifs that have been identified as being like prevalent in genomics. And during my PhD, I mostly focus on sparse matrix, as you will notice soon. And so I will divide like my contribution in three main parts, where you will see there is a clear imbalance in the first part. So the first is like seeing the computation through like high powerful like abstraction. So the computation, the knowledge genome assembly. And then second part is like, how can we exploit hardware, heterogeneous hardware to increase the performance, but also to take advantage of the fact that like systems are getting more and more heterogeneous. So if you have a system that has 8 GPUs per node, we just don't want to use the CPU, and that's it. And the last part is like, it's great to develop, the idea is like, it's great to develop like a scalable and parallel algorithm that can run on thousands of nodes. But then if the final user does not have access to thousands of nodes, that's kind of pointless. We want to be able to have like parallel system be accessible to everybody so that you can actually take advantage of this performance. And these are the three main like topics where I will focus today. Okay, this was kind of overview, and now I'm gonna go a little bit like giving an overview of the actual genome assembly problem as sparse matrix multiplication, and then I will give you 2 examples. So ALBA, that is the name of the software that we developed, uses a very common paradigm to assemble long read assembly. So at high level, what we do is like, we start from the input set of sequences or reads, and then the first things we want to do is called overlap. So the idea is that we want to find matches between every 2 pairs of sequences and trying to figure out how they connect to each other. And this is to build the overlap graph. And then the idea is like, we have this graph that contains a lot of information. And since there is the redundancy in the data and in the way they sequence them, there's going to be like a lot of redundant information in this graph. And it's going to be very hard for us to actually extract what is important and not. So what we want to do is to clean this graph. And so the way we do this is using a transitive reduction that just removes every information that is redundant so that it's not necessary. And then once we have this, the idea is like, we want to extract linear sequences that ideally in a ideal world, we would just extract a chromosome or the whole genome if the genome is a single chromosome. In practice, due to repetition and errors, is a little bit more complicated than that. But the idea is like, from here, we want to extract linear chains that are called contigs, that is the output of many assembler. Then in the state of the art is also typical to add a polishing step in order to try to make these contigs longer and more contiguous. And well, maybe I should have said this earlier, but ALBA stands for like extreme scale long read Berkeley assembler, but it's also a beautiful island off the coast of Tuscany in case you need a vacation spot. And so going back to work. So the idea of ALBA is that we can see the whole computation as computation between sparse matrices. And this is because we use the sparse matrix as core data structure. So rather than having, is there a question? So rather than having like different data structures like throughout the whole computation, what we do is we just use the sparse matrix and then we perform computations between them in order to find the various steps. And this is just like a brief overview of the pipeline. And the 2 main advantages that we have in this case is, first of all, we have greater flexibility and modularity. So at the beginning, I was telling you how hard it is to just change the kind of data that you're using. But with sparse matrices, it's actually pretty easy because like it happened multiple times during the development that we realized that, oh, actually we need one more information that we didn't know since the very beginning. And so we just went back, changed the structure, for example, the non-zero in the matrix and the kind of operation that we do. And that was it. But it was never like a huge pain that you had to, change the whole algorithm to take advantage of new data. And the other advantage is that like from the high performance computing community, we know how to parallelize sparse matrix and sparse matrix computation efficiently. So like we gain in performance and in parallelism because like we use better parallelization strategies, but also like in programmer productivity, since we did not have to like spend a lot of time thinking about how to like parallelize and distribute in memory these very regular like factors. But actually we already had like an idea.
Facciamo un altro giro una volta che siamo qua.
How do I mute everybody? Can I mute people? Okay, cool. Muted. Perfect, sorry. And now this is lost. Okay, so here, just before I move, so the first computation that you see here is K-mer counting. And K-mer counting, I will not go into the details, but I'm just going to give a brief overview because it's important to understand how we move to the sparse matrix realm. And the idea is like we have these input sequences. What we do is we extract K-mers that are a substring of fixed length K. And so for each sequence, we extract all the K-mers, and then what we do, we count them so that what we obtain is this distributed hash tables where we have the K-mer instance as the key, and the value is the number of times that the K-mer appears in the input dataset and where it comes from. So in which reads it appeared. And this is needed because from here, we can move to the sparse matrix realm. So basically, you can see that this hash table is the same as a sparse matrix where we have K-mers as rows and reads or sequences as column. And in this case, the non-zero is telling out that K-mer existed in that read. And so this is the overview of the kind of problem. And now I'm going to go into the details of how we find overlaps between sequences using sparse matrices. So we said that we have this sparse matrix A. So in this case, it's like sequences by K-mers, but we will also have the transpose. So, and what we store in the non-zero is the position of the K-mers. So if you look at this example, we have read 3 that is here and K-mer 2. So K-mer 2 starts at position 16 in read 3, sorry. And so that's what we store here. So it's just an integer. And from here, so we have A and A transpose. So we have reads by K-mers and K-mers by reads. And what we want to do now is to multiply the two in a matrix multiplication. And so if we take R2 and R3 in A transpose as example, and we try to perform a matrix multiplication, what would happen is that in the final output C, matrix C that we call the candidate matrix, we would have for like R2, R3, 537. And we can stay here a few minutes, hours, or weeks and try to figure out what that 537 means in the biology realm. And probably, I mean, I'm sure it will be funny, but probably we will not come up with anything particularly meaningful. And so the idea here is that we can use what's called semi-ring abstraction. And so you know that like in the matrix multiplication, there is an addition operators and a multiply operators when you multiply the two matrices. What we do instead is like we overload these operators using a custom semi-ring to do something that is meaningful for our computation. And so in this case, the output matrix, the non-zero in the output matrix is no more an integer as the two input matrices, but is a more complicated data structure where it's an array of pairs of integers where we store the position of the K-mers and an integer count. And so in this way, what we do is we overload the multiply operators with an assign. And so basically in the output C position 2 or 3, we make a pair of like 15 and 7, that is the position that K-mer 1 has first on read 2 and on read 3. So we make a pair out of that and we store it in the output position. And the addition operation becomes a concatenate. So in this case, R2 and R3 have a second K-mers in common, K2. So we make a pair of those positions as well, and we push back in a vector so that we store both of them, and we increment the count. The reason we have the count is to keep track of how many K-mers we have, and you will say, how you just don't take the size of the array? Well, in distributed memory, we do not want this array to be dynamically sized. So what we do is like we decide how many K-mers to store at compile time. And this case is true because we did like empirical like evaluation and we realized that like having two positions is enough to get like good quality results. And so what happens in practice is like we just store two positions here, and then two reads could have like 30 K-mers in common, and that's fine. We want still to know that information, but we store up to two positions. And so the output is this candidate matrix C where we have initial non-zero. So this is sequence by sequence or reads by reads. And the non-zero is the number of common k-mers, in this case is only one, and the position of that k-mer on the two corresponding reads. And I will not go into the details of the subsequent states of this pairwise alignment, but that's where we need the position of the k-mers, because basically what we want to do is like, okay, we know that these two reads have this k-mer in common, and instead of just align, nucleotide level these two reads, we want to start like from the beginning. We want to start from the seed, because we know that if we would start from exactly the beginning of R1 and R2, they will not match. Like the alignment would be bad. But if we can start from the seed, then we were able to just extend the match and figure out if it's an error or not. And so this is just some recall and precision results for the overlap detection part. So where recall is the amount of good overlaps that we're able to find over the amount of good overlaps in the set, and precision is the amount of good overlaps we found over the total amount of overlaps we found. So both the good ones are not. And of course, like the higher the better in both cases. And in terms of data sets, so we have E. coli and C. elegans. So this is but the interesting things, so two different organisms, but the interesting things here is CCS and CLR. So they're both data sets from Pacific Biosciences, that is a sequencing company. But CCS is a newer technology that has lower error rate, while it's below 0.5%. While CLR is the basically this is the technology I started to work with, and this data set has a 13% error rate. So there is a lot of errors in this data set. And as we can see, ALBA is performing very well on the CCS data. So we almost have 100% both recall and precision. And so this is great. And just if you wondered, it's not that the sparse matrix multiplication makes our precision goes up. What makes our precision and recall performing very being up is the mathematical methodologies that we have developed, that we have included into the algorithm. That I will not talk about that in the presentation, but I'm happy to talk about that offline. But if we look at the CLR, basically we could identify two set of tools. So we have ALBA and NICAP over here, that they have decent precision and recall, and then we have Minmap2 down here that has pretty good recall, but the precision is pretty poor. So it does have a lot of false positives. And for our application, we are very happy with this precision and recall. But since the overlap detection could be used as also another application that is not necessary in our field assembly, one might prefer to have very high recall of Minmap2. But in this case, we are very happy with this performance. And okay. And in terms of runtime performance, so this is a comparison with Dibala-1D. Dibala-1D is being developed by my academic sibling, Marquita Ellis, that she graduated a few years ago. And Dibala-1D is implements this overlap detection in distributed memory using distributed hash tables. And the interesting things here, we can see that both scripts scales pretty well. So they have both a parallel efficiency of around 80% or hundreds of nodes. ALBA is slightly faster, about two times faster. But the interesting thing here that doesn't really appear in the graph is it took significantly less time to develop ALBA than Dibala-1D. And that's the reason why I was mentioning at the beginning about parallelization strategy and sparse matrix multiplication. And this is because we knew how to parallelize sparse matrix computation, so it was just easier for us. We didn't have to spend a lot of time trying to figure out how to efficiently parallelize distributed hash tables. And so this is what's the overlap detection. And now I will go into the details of the second part. So now we have this graph that is messy and pretty. I kind of like this. I was thinking of making a t-shirt out of this. But we have this very messy graph. So the idea is we want to clean it so that it's going to be easier for us to extract linear chains in the end. And the way we do this is using transitive reduction. Transitive reduction is a process that takes a graph, so in this case, our overlap graph R, and makes it into a string graph S. And the definition of string graph is a graph with no redundant edges and vertices. And so I will start talking about the vertex and what's a redundant vertex. So a redundant vertex, if you imagine this being overlapping with, you can see that the sequence 2, R2, is fully contained in R3. And this means that any connection that R2 has, R3 will have it too. So R2 is not needed. So what we do is that we remove R2 from the data set. And this, as you can see, already cleans the graph quite a lot. So it's already like much more like clear. The structure is much more clear than what we've seen before. But if we zoom in, you see there is still a lot of redundancy. So ideally, we want these to be linear chains of vertices. Well, there is still like a lot of redundancy going on. So the way we remove that redundancy is using the procedure to remove redundant edges, since we removed the redundant vertices already. And the first things we do is we take our matrix R, that is the result of the overlap detection. So it's sequence by sequence, and we have k-mers in common and position of the k-mers, and then also like some other things that we developed, that we computed during the alignment that I haven't talked about. But what we want to do here is to slightly change the representation of our non-zero. And so instead of storing, a k-mer in common here in the middle, what we're going to store is the overhang length. So let's say that R1 and R2 overlap. We just store the length of this overhang, and also like the coordinates. And so because the idea is like once we have the linear chains and we want to traverse the graph to concatenate the sequences together, we do not want to like traverse the overlap twice. So we don't want to like say, oh, I go here and then I go here again. Or we want to just read R2 and then concatenate the final part. And so now we need to define, like we define what's a non-zero, but we need to define what's a redundant non-zero in this case. So the idea is like, if you have this graph, you can clearly see that there is redundant information. To go from R1 to R3, you could go through R2, or you could just do one hop and go to R3. But the idea is like, we want to remove one of these two paths, but we need to figure out which one carry less information. And since we remove contained sequences, this little rule that the shorter overhang is a longer overlap holds true. And so that, and you can see it here. So if you look at R2 and R1, this is the length of the overlap in red, and its overhang is 30. And if we look at the competitive overlap between R1 and R3, this is the overlap. It's much shorter, and its overhang is 60 longer. And this rule holds true. And so the idea is like we want to keep the longest overlap and to removing the shortest overhang or suffix. So this is what our graph will look like in the end, because we know that there is more information between R1 and R2 than between R1 and R3. And so we want to remove that, and we can get to R3 through R2. And the way we do this is obviously through sparse matrix multiplication. And so the idea is like we multiply the matrix R, that is that overlap graph, and by itself to find the two hop neighbors. So in the neighbor matrix N. And in this case, we also use semi-ring abstraction. So instead of add and multiply, we use mean N plus. And the way this works is this way. So let's say that we want to go from R1 to R4. So we are looking at the two hop neighbors, two hop path, sorry, to go from R1 to R4. And so one path is between going from R1 to R2 and then from R2 to R4. And so what we do is like our multiply becomes an addition because we want to sum the length of that path. So to go from R1 to R4 to R2 is going to take 100 nucleotides, you could imagine. But then we have a second path, and that's going from R1 to R3 and then from R3 to R4. And here, if we sum it up, the result is 90, so it's shorter. So what we do in the addition operation is we do a mean operation. And so we compare the two parallel two-hop paths, and we take the shortest because that's the one that carries more information with a longer overlap. And so we're going to store that 90 between R1 and R4 in the matrix. And once we have these two hops neighbors matrix N, what we want to do is like we want to compare that element-wise with the original matrix R. So in doing this operation, there's no communication involving distributed memory because we are just doing element-wise. And so the idea is like we want to see, like ideally, like the concept is we want to remove any edge in the original matrix R, so the one hop edge that like has a path in the N matrix that is equivalent or smaller like, or smaller, because the idea is like, okay, there, like, if it's there, if in N there is like a non-zero element wise that is equal or that is smaller, sorry, then there is a better path or an equivalent path that I can take with 2 hops rather than 1. So that's fine. I can remove it from the original matrix. So in this case, to go from R1 to R3, we have a 2-hop neighbors that is better. So going through R1 to R2 and then to R2 to R3. And so we can mark R1 to like R3 to R1, sorry, as a transitive here, and the same applies here. And then what we do is like, okay, now we have this matrix I where we have the transitive edges marked. What we do is multiply element-wise again, the logical negation of this matrix. So now we have zeros over here times the original matrix R. And this will remove the transitive edges from the matrix, just leaving the string matrix R, the string matrix S. And in practice, what happens is that like this, like few operations, so from R squaring to here, we will do in a loop in order to remove, like it's a, like there will be many iterations to remove the 2, 3, 4, 5 hops neighbors until we don't have transitive edges anymore. And this, the matrix multiplication at the beginning is the most, like compute intensive. Okay, and so here we can see this was the intermediate overlap graph. So this is the overlap graph where we already removed the redundant edges. And then whoever is speaking can please mute themselves. Okay. And so what we have here is like overlap graph without redundant edges. And then here we have the string graph. So if we zoom in over here, we can see that now all that redundancy in the path is removed and we just have redundant edges. And so now I'm not going to go into the details of the next part because we don't have time, but I will just give you a brief overview of, you know, how we go from that to the linear chains that are called the contigs. I actually think it's my family that is doing this noise. So the idea is that we have this graph that is our string graph at this point. The first thing we want to do is to identify those that are like linear chains. And so the first step that we do is to identify the branches. So, you know, like extracting these linear chains is what we want, but we need first to identify where there are branching points. So we identify branches and we remove the branches from the matrix or from the graph. And then so this is what we obtain. And then once we have this like linear components in the matrix, what we do is we want to divide these components and redistributed them across processors so that the load is balanced. So the idea is like we use the contig size, so the number of reads that are in a contig, to decide how many reads to send to processor 1, 2, and 3, etc. So in this case, if we would have 2 processes in our computation, we could divide easily contig orange and green on processor 0 and contig blue on processor 1. And the idea here is that we want to have linear components on a single processor so that then we can concatenate and perform local assembly locally on each processor without communications. And so this is what in my head represented a sequence. And maybe like I should have pointed out that like the reason why we want to do this is that when we have this, you know, the first 2 yellow like vertices, not yellow, orange, could be on processor 0, and the third could be on processor like 2 or 8. So like there's no guarantee that like all of these will be on the same processor at this stage. So that's why we want to do this type of communication. Okay, so, and you know, you can imagine there is a lot of matrix computation going on here, but for now we'll just skip over it. And so what we obtain, we move from the transitive reduction to the contig generation. So this is what like an output would look like, where we have like many linear chains, and adding a polishing step that is something we're working on. The idea is to have like then longer contigs and making like more contiguous. And in terms of performance, so this is a few scaling. I'm going to show a few performance results on different data sets. These are all, so C. elegans and Sativa, this derives is, they're both like CCS data sets, so low error rate data set. And here we can see the scaling of ALBA on both Corey Haswell and Summit CPU on up to like 128 nodes. And then here is the breakdown of the performance. So here we can see how the alignment, that is the gray part, is taking quite a lot of time on both machines. And then we can see how alignment and overlap detection, that is the first things I was talking about like using sparse matrices, scales pretty well. And then if we look at the top here, we have transient reduction and context generation. Then on Corey Haswell especially is particularly fast. So the scaling is not like as good as the other components, but the computation is much faster. Okay, and here is one more example with a bigger data set. So this is human sapiens. So this is like human data set, and this is a CLR data set. So this is like a higher error rate. And we can see that the scaling on Summit is very good. It's like around 90%. And this is the breakdown that, it's not saying anything particularly new. The alignment is taking quite a lot, while transient reduction and context extraction are fairly fast procedures. And this is going, okay. And so with this, I conclude like the part on sparse matrix and genomics computation. And I just want to talk briefly about the high performance computing in the cloud, so it will not take long. But the idea here is that, I mentioned at the beginning that the goal of my dissertation is to be able to use this like parallel systems for de novo genome assembly, and in the long term for science discovery in general. So we want to make it more accessible. And I've shown here how ALBA can perform overlap and layout phases, and also like the content phase, because that takes very little, in less than 10 minutes versus like days for like big data sets. But we have to consider that like to get these results, we use like 100 nodes on a supercomputer with low latency network. So we still have to keep that in mind. And so the idea is like, how can we make these resources more accessible to everybody? And kind of like, because the idea of supercomputing is like, it's not that easy, maybe to get access to it. You might need to be in the exact, in the right research community, something that like interests like DOE, for example, or like the institution that like, that's maintaining a supercomputer. So it might not be that easy for everybody to just, hey, I need like 1,000 nodes, how can I get that? And so one like, like easy like solution one would think is like, can we use the cloud? Like everybody can access it. Like, again, like you might use research credit or you might pay for it, but like it's very easy to access. And so, but the question is like, can we use the cloud for like scientific computation? So can we get the same performance? Because again, like we can have thousands of nodes, but then if the performance are not the same, then at that point, like you don't want to pay for that. And if you look at the literature until 2018, and I've been doing this work starting like mid 2020, but if you look at the literature until 2018, it's pretty clear that like cloud is great for a few things, but like when it comes to computation that is communication intensive or that requires low latency network, then it's way behind traditional supercomputing. And so like the question I asked myself was like, is that true today, where today was 2020? And the answer was actually pretty interesting. Was very excited to work on this. And so I ran a whole bunch of like micro benchmark and experiments on two sets of machines. So Corey Haswell and Corey Kennel, that are two partitions of a supercomputer, and that we have here up the hill, and two instances on AWS, R5 and C5. So R5 is memory optimized and C5 is compute optimized. I just wanted to, to have two different machines. And before getting these results, I did run like a whole bunch of like results on a single node and single core levels, just to make sure that, the hardware I was comparing, like, it was a fair comparison. I just didn't want to just maybe get some results here and not knowing what was going on at the single node level that could have affected this. But concluded that the single node performance were, comparable, then, and actually like the cloud was doing a little bit better, but also like it was a newer system. So that was not surprising. But what's very interesting here is looking at the network performance. So this is an MPI all-to-all latency on 2 nodes here and on 8 nodes here using 32 MPI processes per node. And what we can see here is that, well, Corey Haswell is the machine doing better, but like doing best, but like the cloud, that is this orange and reddish lines, is not that far away, especially for like large message sizes. That is usually what you want when you're designing an algorithm. And what's even more interesting is that when you increase the concurrency, so when you increase the node, you know, historically one would expect that the gap to get wider, but actually the gap is getting like smaller, especially for the R5 instance. That again is not surprising because the network performance of the R5 is higher than the C5. So it's not surprising that R5 is doing better here. And this represents like a huge improvement with respect to the results that we have seen in the literature until now. And this is reflected also in the application performance. So here I picked n-body simulation and fast Fourier transfer. So n-body is very compute intensive, while fast Fourier transfer is more communication intensive. And if we look at the performance of the n-body, like one would have expected that the performance would have been better on the cloud because it's very compute intensive, and the cloud has always been good at that. But it's so like, you know, the fact that like R5 and C5 are faster per se is not that surprising. But what's still very interesting is that if we look at the communication performance, that is the pink red bar, like layer at the top of the bar, it's actually better than the supercomputer, except for like 8 nodes. So this is actually like very interesting, although like their runtime performance is not surprising. And the true interesting results is on the FFT. Like FFT used to be significantly slower on the cloud, like even up to 40 times slower on the cloud than on the supercomputers. So here, seeing the R5 doing like being better than the supercomputer, also in terms of communication performance, it's very interesting. And even if we look at the C5, it is slower, but like not even a factor of 2. So it's still like a huge improvement with respect to what we have seen in the state of the art. And so, and okay, one more thing I want to notice is like this scale is still pretty modest. So we are not talking about like, you know, hundreds or thousands of nodes, but this is still like, you know, the state of the art also use like just like 8 to 16 nodes. So it's still like a very like nice results. And if you think about the reality, you know, like most of, maybe not most, but like a good chunk of application and users might not need like 1,000s, but they could already benefit quite a lot of being able to use, you know, a few dozens of nodes to increase the runtime, to decrease the runtime of their computation. So this is like very interesting. And so like basically the answer to my question is like, yes, we can use the cloud, or at least it's like at the start of like, you know, a paradigm shift in high performance computing. And I'm sure that like this will become more and more prominent as we go forward. And I'm also just very happy that like this work then attracted the interest of Google, IBM, and Microsoft, that I know so Amazon, that gave us like extra funding and say, hey, can you look at our cloud as well? And so far I haven't been able to look just at Google, and I can confirm that Google is also doing pretty well, like on the same line in Amazon. Okay, and with this, I conclude you know, basically my talk. I'm just gonna go briefly over the conclusion and future works. So today I talk about like 2 main parts of my dissertation. So I introduced ALBA, that is a long read to long read de novo genome assembler implementing distributed memory uses sparse matrices, and also talk about how computing is opening a paradigm shift in high performance computing and how it could be used in the future to improve access to high performance resources for scientific computing. And in terms of future works, what I plan to do is to identify big data science challenges and try to figure out how we can map this, you know, identify if there are like computational motifs, and how we can map this on this like higher level primitives and make it faster and easier to develop. And so this is not just an advantage, you know, from like the programmer and like application perspective, but if you also think about this from like a hardware perspective or like a programming language perspective, if you're able to map multiple different computations on the same computational primitive, then it becomes much easier to port the computation to hardware or to build a DSL, for example, for that. And so not just hardware that we have right now, but also, build a novel hardware, because right now maybe it doesn't make sense to build like, a hardware for like my specific de novo genome assembler, because it's like, that might be like way too much work. And even for a company, you don't have the return on investment. But if I can show you that like there are like many applications in genomics or other computational sciences that would benefit from this, then building hardware for this does make sense, even from an industry perspective, not just research, like academic perspective. And the long-term goal is being able to guide the design of like systems where we can combine the capabilities of supercomputers at a very large scale with availability and reliability that we can find in the cloud. And I just, and with this, basically, I concluded my talk. Now I just wanted to do like some closing remarks. And one goes to my dog, Ziger, that recently passed away. I feel like many of you have seen him around, and he has been like a huge source of support and love throughout grad school, even before the pandemic, even more during the pandemic. So I just, I think this dissertation goes to him as well. He listened to me a lot. So I miss him a lot. He was a very good dog. And like the good things, like a new chapter is starting. And so I'm very excited to say that I will be joining Cornell as an assistant professor starting next January. And in this, so I hope to keep collaborating with Berkeley and getting new collaboration. I'm very excited. Everybody's warning me about the weather, so I'm still trying to be okay with that. But the nice thing is like I will have a new companion coming with me to Ithaca. He still doesn't know that he will live in the snow, but he will be in that known for a little while more. This is Mahler. And I thought about bringing him here, but besides it's not allowed, it's kind of in like Velociraptor phase of puppiness. So it's like, it's just not fun to be around always. But hey, it will grow out of that. But until December, I will be in Berkeley as a project scientist at the Lawrence Berkeley Lab. So, if you want to chat with me or just hang out, I will be around. And so this is concluded future works and like my presentation. And I just want to say thank you to everybody, to my advisor, Kathy and Aiden, and to my committee, also Dan and Jim, and like all the people that, I've met during these years, and both like, in the university and not like in grad school. And it's just been amazing. And, I wish like, if I could do it again, honestly, I would do it again. There will be like ups and downs, and it's not always been easy, but I just take with me a very, very positive experience here at Berkeley. And you hear a lot of things also about academia and PhDs, and I just wish that everybody could have had the experience I had, because it's been great. So thank you very much to everybody. And if there is any questions, I will be happy to take it now, offline, or yeah. Thank you very much. Yep.
So you showed the puzzle piece analogy at the beginning. And then, of course, the genomics problem is linear.
Mhm.
The genome is linear. And so you have this graph, which is mostly strings, but then you have the band points.
Mhm.
Limited, but they're far few and far between. And I wonder if there's a two-dimensional or higher dimensional generalization of this. Or
What-
maybe there's a kind of a surface that you're trying to model, and you have local relationships on the surface, but there's a minimal set. And the same way you did transitive reduction,
Mhm.
you want to find out not that this puzzle piece is known to be 3 units away,
Mhm.
but that you can reach it by intermediate puzzle pieces. It's kind of fuzzy in my mind, but I
Yeah.
think there's a lot of situations where
But you're still thinking at a single species or like multiple species? Like, sorry, multiple like individuals or multiple genomes?
I'm outside of genome.
On thousands of genomes, okay.
Like I have a
Yeah. Yeah, no, like there might be like, and it might, it might use like tensors, like that's already like basically higher dimensional representations of matrices. So maybe there's like, I honestly haven't thought about that, like about the higher dimension applications, but there might be. Might be interesting.
So protein folding is definitely a higher dimensional thing.
Sure.
Is that a possible example?
I think, well, I mean, I feel like protein, it's more like, it feels to me like more of an optimization problem than like you can find just like with like similarity. But maybe if you would have like a structure, like, I mean, like I would imagine like if you just think about the structure of the problem, maybe that could be like if we just look like the folding process is more like finding like local minimum of energy or like, but if you could compare protein structures that could be possibly represented as a tensor because you want to be able to have like a spatial and not just like two-dimensional representation of the protein, and that might like for homology in protein structure that might be interesting application. But I think that like the protein folding process itself, it seems to me more like an optimization problem than homology, because you have to consider like all the like spatial movements and the minimization of energy.
Very nice work and
Thank you.
very clear thought. So I have a few questions. One is when you calculated the matrix of I think you plotted the number of tumors in the read.
Mhm.
What's the size of it?
So the size of K changes based on the error rate in the data set. And for example, for the low error rate data set, we used 31. And for the high error rate data set, like we use 17s. But like amongst the, mathematical methodology, as just briefly mentioned, we develop like a Markov chain model that can be based on like the size of like it can basically give based on the error rate of the data set and the length of the overlap that we want to be able to detect. It can give us the optimal K-mer length so that it's not too short where we would have a lot of repetitions, but not too long that will miss good overlap due to errors.
When you say high error rate and the low error rate, I think the low error rate is the short read or high five.
Yeah, so like short read have like lower rate, but like the CCS technology from Pacific Biosciences, I've been able to reach in the past like couple of years, like very low, like close to like Illumina short reads error rate. So like in my work, I just use long read technology. So like we're talking about like an average of like 10,000 best pairs of nucleotides in read length. But CCS has like a very like low error rate, similar to short read.
So when you use long read, what's the high error rate read and so it depends. I think like for long read, file and then apply the two properties up.
Yeah. Yeah, exactly. Like, so here we just like in this data set, we just use Pacific Biosciences. So we didn't use Oxford Nanopore, but of Pacific Biosciences, we use CLR, that is the high error rate, so like 13-15%, and the CCS, that is low error rate, like closer to Illumina. I think they've been around a lot, but it got cheaper. Dan can correct me in the past few years. So now people are starting to use it.
And also, I think when you remove the redundant bits, I think maybe you could change the coverage. I know in metagenomics data to assembly coverage.
Yeah.
But I think your work is currently for like information of not.
No, right now we are not doing metagenomes, but it's something that we have like been talking about multiple times. And I agree that like in the transitive reduction, that's something that we actually consider also for single genomes to make it maybe the assembly of context easier. What we could do is like when we remove redundant information, rather than just remove it, we could keep track of what we remove so that we know that a path has possibly a higher weight or coverage than the others.
Like to assembly, the coverage information still important since it may represent at least content is repetitive in the genome of one of the.
Yeah, I do have like some, let me show here, somewhere. I do have like some assembly. So this is, I had like some, if I go and present it more, it doesn't work. Okay, so I have here, well, this is just some runtime with a state of the art, but in terms of like, so what we can see here, our context. So the context itself, so we have more context and like shorter than for example, and the reason is that like we do not have like a polishing step right now, so it's kind of expected. But what is nice is that if you look at the completeness, so like, you know, how much genome we are able to cover with our context, it's still very competitive, even higher. So like we're able to find like a good chunk of the genomes, like to cover a good chunk of genome. I don't know if that was a question, maybe.
Yeah.
Okay, great. So definitely like what we're working on is to improve these two metrics so that we can get like longer, more continuous counting. But yeah, but like in terms of coverage, we have pretty good performance in covering the result, like in covering the whole genome.
And just one more
Go for it.
about when you remove some read, you wanna remove read with shorter or hand and then longer or left, right?
Mhm.
But I think even in long read, the length of read is not fixed. So sometimes with short or hand is not always longer or left, right?
Yeah, so we had this discussion, and it would be true if we will not be removing contain reads. If you remove contain reads, it is like proven that you can that a shorter hoverang is always a longer, so a shorter hoverang is a longer overlap, and vice versa. If we would not be removing contain read, then I agree, then it would not hold true.
Also, with respect to depth, the length of the overhang is proportional to the reciprocal, is inversely proportional to the depth of that application. Right, the more reads, the shorter the.
Yeah, exactly.
Steps. So you have some of that information. That's we can. So we'll go back.
That's correct, right? Let me see if I can read. Okay. Thank you. Thank you. If I don't know, if we are like right in time, if there is any other question, I'm happy to answer. Or otherwise, just thank you very much for being here. Thank you.
Giulia, I have a question.
Go for it.
So I noticed at the beginning of your talk, oh, sorry, by the way, thanks for a very nice talk.
Yeah.
I noticed at the beginning, you were talking about overloading matrix multiplication to find the common number of k-mers in two reads.
Mm-hmm.
And you noted that you stored, that it was sufficient to store only two common k-mers.
Mm-hmm.
And I was curious about how the speed of this operation scales with the number of k-mers that you store. And I guess also how the speed of the operation depend, like when you overload it with different types of operations that you would like to do.
Mm-hmm.
So say instead of adding addition and multiplication, as you noted before, if you wanted to do something like significantly more complicated. I'm curious, yeah, how you expect the speed of your algorithm to scale in those situations.
Yeah. Okay. So regarding the first part about the number of k-mers, so I don't have number exactly, but like I do not remember to see like there's like a increase in runtime just for storing more k-mers. That was more like the amount of space that we were using to store the matrix. Then if we would have stored like, let's say like 15 k-mers rather than 2, then we could have this could have affected the runtime of the alignment later on, because maybe we would have run alignment on 15 times for each pair of read rather than 2 times for each pair of read or something like that. And in practice, we weren't doing that. But so that is something, but like the storing more k-mer itself, it does not affect performance. And in terms of like operation between the matrices, I would expect that to like vary based on the operation that you are doing. Like if you're doing like say that like if the non-zero, if you're overloading the operators with a like a very compute intensive operators, then like that would have affect performance. So the kind of operation that you're doing would do that. But usually the kind of operation that you're doing, like that at least we're doing over here, is it does not take significant amount of time. The sparse matrix multiplication it's very, very fast. Does that answer your question?
Okay, yeah, so you said that fundamentally the speed of the algorithm doesn't change with how many k-mers that you store, only the amount of memory that it takes. Am I correct in that?
Yeah, then like what you could affect is
The next steps, yeah.
Exactly. Like based on what you do with those k-mers, then you might have a more or less significant increase in runtime based on what you do.
Okay, so then I guess my follow-up question is like, would you say that the performance scales linearly with the intensivity of the operation that's going on at, right? Because you're sort of changing the matrix multiply operation column by column. So you have an operation for each pair of columns. And we're discussing like making that operation significantly more complicated. And so my question is, does your algorithm scale linearly with the speed of that column-wise operation?
Well, the algorithm scales linearly. If you would take like significantly much, like, you know, significantly much heavier, like almost linearly. If you like the operation that you're doing would take significantly much less time, like much more time, then, you know, you would have an increased runtime.
Is it linear in that operation time for the column-wise operation?
Yeah.
Okay. Thank you very much.
Of course. Any more questions? Thank you. Okay, thank you, everybody. Stop here. Okay. Thank you.
I'm Yano from Harvard University.
Mhm.
I just visited here and I read your paper a few days online.
Thank you.
I read your paper a few days online and
Oh,
then
that's-
I know this topic, so I can.
Oh, that's amazing.
Yes, it's amazing.
Yeah.
Great. Yeah. I also worked on genomic data before I was in UCSD health
Mhm.
wellness lab. Yeah, and we worked on something on human genome, and now I work on metagenomics.
Nice. Yeah, so like my group has like been doing like a lot of metagenomics with short reads
Oh,
so
really?
far. Yeah, I can give you like some reference, or like we can talk about that.
Yes.
And the plan is definitely to move from like single genome to use this approach for metagenomics as
Oh,
well.
nice.
Of course, like one of the main difference would be the k-mer selection, right? Right now we have like a k-mer selection, not just the size, but also the set of k-mers that we retain. For example, we want to remove k-mers that are too repetitive, but of course, you know, to do these procedures, we use the depth and the k-mer size and error rate. But as you mentioned, like when you have metagenomes, like you don't have like depth information, so then you can not use that. So like one interesting thing is like, okay, if we move to metagenome, what it will look like. And I think that honestly, I think that like extending the procedure to metagenomes, it will not be like from a software engineering point of view, a lot of work because the algorithm is very flexible. And so that I think that would not require much. But what we will need to think about is like, okay, now how we select k-mers. And maybe the answer is just we just use everything and we'll figure out later. I don't know. And then what I had in my mind was, okay, what we could do is like we will still get to the string graph. So like a clean graph, and then try to partition that so that, like, for example, using clustering, maybe, and so that we can, you know, separate the genomes as much as possible, and then being able to slot and assemble them.
In my current lab, we also use universal data set or minimize.
Oh yeah,
to do parallelize. So yeah, I think I'm not sure it's possible to combine.
Yes, it is. It is absolutely possible. Yeah. So basically, the only thing that will change is that instead of having like k-mers by reads, you will have a minimizer by reads or like whatever. And it was actually funny because we were thinking about yesterday with my advisor and a student working with me how we do the contig extension, and that will basically again be like branch contigs, matrix multiplication, and like it's funny. I think you can present a lot.
Yeah, okay. I will be here for another 2 weeks, so I think the research is very related, and yeah, I would like to.
Yeah, let's set up a meetings. Do you have my emails?
No.
Okay. Oh,
I can.
I was one.
We can have a coffee together sometime.
Yes, absolutely. Like I'm here until I will leave for vacation
Mhm.
on the 11th, on the 12th, but until then I'm here.
Great, good. Okay. Can you write the email?
Yes. Sorry, I'm gonna put it here. This one is okay.
Thank you.
Just give me an email and like we'll figure it out.
Okay,
Perfect.
thank you.
Have a good day.
So see you later.
Yeah. Thank you. Okay. Yes, you can.